Good afternoon all. Welcome you all to the teleconference program organized by Department of Chemistry, Dr. B.R. Ambedkar Open University. Today we are going to discuss about the asymmetric synthesis topic. This topic belongs to Chemistry 5, Block 3, BSc third year. It is also covers a part of Block 3, Course 6, MSc Chemistry also. This program is of 60 minutes. In this 60 minutes, we are going to discuss about the topic in the first 40 minutes. Later, remaining 20 minutes, we will take the questions from the audience. During the 20 minutes time, we will answer whatever the question regarding the subject we will explain. For knowing the answers for your doubts, please call us 040-23680-456, and also you can put your doubts in the chat box of our YouTube channel. Right. Now coming to the topic, asymmetric synthesis. To explain these topics, we have two eminent personalities are with us. In that, Dr. J. Mphan Babu, University College of Science, Hyderabad. Dr. M.D. Areef, he is the senior faculty member, expert in JEE mains. Now coming to the topic, asymmetric synthesis. What is asymmetric synthesis? What is its significance? What is the need to we learn that topic? First we coming to the asymmetric synthesis. What is the asymmetric synthesis? This is the part of organic chemistry. Not only in organic, in the entire chemistry it is the one of the branch. In that branch it deals with the several reactions. In that reactions there is a clear indication of formation of particular stereoisomer. It is the more amount in the reaction when we compare to its corresponding stereoisomer. This is called asymmetric synthesis. In this asymmetric synthesis, we will conduct several reactions to synthesize several stereoisomers like enantiomers and diastereomers. Right. What is the use of these products? In the most of the organic compounds, those are associated with the biological systems. These biological systems are specifically recognized the organic molecule if the organic molecules are stereoisomers. For example, in the history, thalidomide is one of the drug. It is used for the sedative. Actually, it is existing in the form of two enantiomeric compounds. One of the enantiomer is it is a potent towards the sedative effect, and another one is it causes the birth defects in the pregnancy women. Due to that reason, the existence of these compounds is due to we are neglecting the characterization of the compound during the synthesis. When the drug is formulation takes place, these two molecules are existing in taking drug. Due to that reason, this drug is withdrawn from the market. Right. Here these two compounds are enantiomers. These two enantiomers we are not able to characterize whenever we are using in the broad area. It causes the several adverse effects. Due to that reason, we need to concentrate on the synthesis during the compound. This synthesis is called asymmetric synthesis. This asymmetric synthesis holds the grip to control the synthesis of that chiral compound, that controls the synthesis of that particular chiral compound. Therefore, we need to concentrate the methods of the asymmetric synthesis. We need to understand the process of asymmetric synthesis. We need to understand the various concepts of these asymmetric synthesis concepts. Now, I am asking Dr. J. Mphan Babu garu, please explain what is topicity, how these different terms are classified or defined based on the topicity.
Yeah. So, first of all, generally here the asymmetric synthesis means where the creation of a chiral center in a achiral compound here. If any achiral substrate is there, so by substituting or by introducing up some ligand compound or the any groups here, so we are going to create a chiral means we are introducing a chiral center on that compound. So this process is called the asymmetric synthesis, and in this asymmetric synthesis where you can see the stereochemistry, so it will be differentiate in the stereochemistry. Generally if you take this particular compound here, so propionic acid, so this propionic acid where it is a achiral in nature, where it is carrying the one COOH group here and CH3 group and two hydrogens, where these two hydrogens are homotopic, right? Homotopic in the sense both are the same atoms here. So it is a achiral in nature. So what we are going to do here, so we are substituting, means we are replacing one of the hydrogen with the external ligand compound. Then what happens here, so it is becoming chiral nature. So all the groups are different, okay. So it is called, it is a chiral. And one more thing is, when we are getting the compound, when we are doing the reaction here, so if we are getting the products in a equal ratio, then it is not a asymmetric synthesis here. And if you get the products in a unequal ratio, then we called it is a asymmetric synthesis. Or if you get only one product in 100% one product here, then also we called it is a asymmetric synthesis. So in this asymmetric synthesis, to understand the asymmetric synthesis, so we need to understand some terminology involved in the asymmetric synthesis topic here. So first we will see the homomorphic ligands. Homomorphic ligands means homo in the sense same, and morphic means the morphology of the atoms here. Morphology means the nature of the atoms here. So how these two atoms or the four atoms are interrelated, what is the relation between the atoms, right? So we will see the relationship between these atoms here. So this is called the toposity. Okay, so in the toposity we have the two types of compounds we will take here. So one is the homomorphic or the homotopic ligands and homomorphic phases. Homomorphic or the homotopic ligands means where you can see the sp3 hybridized carbon which is attached with the different groups here, or the same groups or the different group. And in the homomorphic or the homotopic phases where you can have the sp2 hybridized carbons which are having only two groups aligned on that particular compound, and we will see the space, we will see the space around that compound here, that is the top phase or the bottom phase here. So this kind of nature will be explained on this particular homotopic phases. Here first we will go with this particular homotopic ligands, and here to see the relationship between the atoms, whether these are homotopic or the heterotopic. So we will apply the two criteria here. One is a substitution criteria and another is a symmetry criteria. So for example, so we will go with one model here where this is the olefin compound. So in the olefin compound you can see this alkene olefin compound. So where the four hydrogens, okay, on C1 carbon you can see the two hydrogens here, on C2 carbon you can see the two hydrogens. So total four hydrogens attached on this particular olefin compound. Now these two hydrogens are same and these two hydrogens are same. So these two hydrogens said to be the homotopic and these two hydrogens are said to be the homotopic pairs. Now to substitution of this one of the hydrogen or the ligand here with the different third molecule here, then what is the relationship that substituted atom with the rest of the atoms, right. So, for example, here we are going to replace this particular hydrogen with another the different atom here, then what is happening? For example, on C1 carbon we replaced one hydrogen with the different group atom or the group. For example, we are replaced with this hydrogen with chlorine, just to assume it is a chlorine here. Then what happens here? The chloro-olefin, right. Then one more, in the another operation we are going to replace, right, the hydrogen from the C2 carbon here, right. So, we are keeping the this C1 hydrogen same on same place here, and on C2 carbon hydrogen we are going to replace. Then what happens here? Now we get the chlorine on the C2 carbon. Earlier this chlorine is on the C1 carbon, now it is on the C2 carbon. Now you see the both the operations, right. So, when the replacement of this chlorine on, when it is on the C1 carbon and after attachment on the C2 carbon. Okay. So, whether these two are same or not, these two molecules or the products are same or not here. So, now you see generally these two are the same compound here, okay, because when you are rotating this molecule, when you are rotating this molecule by C2 axis, symmetry axis here, like when you rotate 180 degrees, right. So, for example, here we are rotating 90 degrees here, then one more operation we are doing, so C1 and C2. So, when you apply the Cn axis here, then what happens here? So, we get the same configuration. So, now you see, you can say that these two compounds are same. So, these are the homotopy ligands here. Now, it is clear, these two are the, all the hydrogens are homotopic in the nature. And one more compound you can take, for example, if any tetrahedral compound is, you are going to take here, right. So, here also same, this is the tetrahedral carbon where the sp3 carbon here. So, where the 4, just to assume here the 4 atoms are same. Now, we are replacing one of the hydrogen with this the different atom here, then what happens here? So, for example, you assume it is a chlorine or the bromine, you take bromine it as, right. So, this is bromomethane, okay. So, we are replacing C1 hydrogens, right. You label the 4 hydrogens with A, B, C, D. So, first we are replace the H1, okay, HA, for example, HA hydrogen with bromine. So, we get this configuration. In the second operation, we are replacing the HB hydrogen here, then this bromine comes here. In the third operation, we are replacing the this particular HC hydrogen, then the bromine comes here, and in the fourth operation, we are replacing this HD hydrogen, then this bromine comes here, right. So, all the configuration which are obtained after replacement of the hydrogens with the different atom, all are same. So, we said this is the homotopic ligand here, okay. And so, you can take some more examples here. So, here is a where the chloromethane and chloroform also. In the chloroform, where these 3 chlorines are the equivalent. So, these are the homotopic, these 3 chlorines are the homotopic here. And in this particular active tartaric acid, where this hydroxy and this hydroxy, right, these two are in the trans direction, where these 2 hydroxy groups are same. So, these 2 hydroxy groups are the homotopic ligands, and these 2 hydrogens are the homotopic ligands. And here the top acid group and bottom acid group, these 2 are said to be the homotopic here, because these are the, in the isolation form, these are the same, okay. So, structurally these are the same. So, we call these are the homotopic ligands here. And if you take this particular cyclohexane configuration here, so you can see very interesting conformation of this cyclohexane here, right. So, you can see there are 12 hydrogens are attached on this particular cyclohexane conformation, and these 12 hydrogens are equivalent and the same at room temperature, and at very low temperature. So, 6 hydrogens are different and another 6 hydrogens are different. That means, you can see the two types of homotopic ligands are present in this particular cyclohexane. So, why we are getting the why the 12 hydrogens are same at room temperature means, so at room temperature a rapid interconversion of the cyclohexane conformation is done. That means, axial to equatorial and equatorial to axial interconversion is done. That is why all the hydrogens are lies in the same environment. So, there is no differentiation in the hydrogens here, but at the low temperature like 0 degrees or 0 to 5 degrees here, at this very low temperature. So, 6 hydrogens are, it is oriented as a axial direction here, axial means towards upwards here, and 6 hydrogens are oriented downwards, that is a equatorial direction. So, you can see the two types of homotopic ligands here. So, these are the homotopic ligands. Now, we will see the homotopic phases. So, here the phases, homotopic phases generally we will encounter in the unsaturated compounds here. So, in the unsaturated compounds generally you can see just this is the carbonyl group here, right. So, in the carbonyl group this is a carbon double bond oxygen here. So, CO, this is in the carbonyl group. So, where it is attached with two hydrogens are the two groups, whatever you can take it as a hydrogen or the any group, methyl or propyl, phenyl, any group here is attached on this one. Now, here it have the two phases here, it have the two phases, this is the top phase and this is the bottom phase here. Now, the hypothetical substitution or the hypothetical addition of any reagent on this particular carbonyl compound, it leads to formation of a product which is giving the configuration either homotopic or the heterotopic here. So, we will see the relationship. So, after hypothetical addition or the substitution, the obtained product whether it is having the homotopic nature or the heterotopic nature. Okay. So, for example, here we are taking, just to assume it is the acetone compound here. So, in the acetone compound you know that two methyl groups are attached to the CO, central CO carbon group here, carbonyl group here. Now, we are going to react with this carbonyl group with the methyl magnesium halide, Grignard reagent, we called it is a Grignard reagent. So, when the this particular acetone is treated with the methyl magnesium halide, so here this particular methyl group is substitute on this, it is add on this particular carbonyl group and we will get particular the product which is the tetrahedral compound which is having the this kind of configuration. And one more means here the choice is when the Grignard reagent, so it may be attack on this carbonyl group either from the top phase here or it may be attack from the bottom phase. So, when it is attacking from the top phase we will get one configuration, when it is attached on the bottom phase we will get the another configuration. So, after the formation we will see whether these two are same or not here. Now, here basically the acetone is carrying the two methyl groups, both are the homotopic nature. So, obviously the product obtained in this substitution reaction or the addition reaction will get the homomers. So, these two products are the homomers, that means homotopic in the nature. And one more example we will see that cis 2 butene, we will take the cis 2 butene here. So, this is the cis 2 butene where you can so this is the olefinic compound. So, in the unsaturated carbonyl and unsaturated olefinic compounds also we can see the phases here. Okay. Now, in this just to assume it is a cis 2 butene, now we are going to do the epoxidation reaction with peroxide, okay, MCPBA here, metachloroperbenzoic acid. So when we are treating this particular olefinic compound, cis-2-butene compound with MCPBA, so we get the epoxide derivative here, the epoxide product, and here also the two scopes are there. The epoxide means the MCPBA, right? So this peracid here, it may be attacked from the top phase or it may be attacked from the bottom phase here. So when it is attacked from the top phase here, so we will get one epoxide derivative. When it is attacked from the bottom phase, we get the another derivative here. And upon rotation of these two epoxides, okay, when we are applying the C2 symmetry here, so we get the same compound.
Yes. Homomers will be generated.
So we can say these are the homotopic phases here. Okay. Now you can apply this particular homotopic phases to the lone pair electron compounds also. So generally here you can see in the dimethyl sulfide, so where the sulfur heteroatom is carrying the two lone pair electrons. So these two lone pair electrons are said to be the homotopic phases here. Here also upon oxidation, sulfur oxidation, so we will get the oxide derivative, which both are the homotopic product is obtained here. Okay. Then we are going to the heterotopic units or the heterotopic ligands here. So generally here the heterotopic means, hetero means different and topos means the location or the place here. So heterotopic means the atoms attached at the different places or the different positions here. Okay. So in the heterotopic units or the heterotopic ligands here, so here also we will follow the two criteria like substitution criteria and symmetric criteria here. So in this particular heterotopic ligands, we will take the propane. We will take the propane compound here. We are taking the N-propane compound, which are having the 6 hydrogens attached on this particular central carbons here. Now we are applying the replacement of the means substitution criteria to this particular N-propane, where we are substituting the one of the hydrogen from C1 carbon with the chlorine. Then what happens here when the C1 carbon hydrogen is replaced with the chlorine? So on C1's replacement, so what we are getting, right? So 1 chloropropane, and in the next operation where we are doing the replacement of the C2 hydrogen with the chlorine, then we get the 2 chloropropane here. So these two compounds are structurally different. These are not the homotopic here, because here is a C1 means 1 chloropropane, here is a 2 chloropropane. So both are the positional isomers here, constitutional isomers here. So these are not the homotopic in the nature here. So in the asymmetric synthesis, generally for the structurally heterotopic ligands, there is no much significance here, because the the asymmetric synthesis deals with the stereochemistry here. So stereochemistry generally deals with the atoms attached in the space or the spatially attached atoms here. So there is no much importance of the significance of your structurally heterotopic units. So we are moving to the stereo heterotopic units here. So in the stereo heterotopic units, we have the two kinds of terminologies, like one is the enantiotopic ligands and diastereotopic ligands here. So in the stereo heterotopic units, first we will see the enantiotopic ligands. So in the enantiotopic ligands, same here also we will go follow the two criteria like symmetry criteria and substitution criteria. Here also we get the 4 groups on the central carbon atom, but the relationship of the two hydrogens are whether it is homotopic or the heterotopic. So we are going to find out whether these HA hydrogen and HB hydrogens, you can see in this particular right. So here the in this particular compound,
Propionic acid.
so propionic acid. So whether these HA, the labeled HA and HB hydrogens, whether these are homotopic or the heterotopic here. Okay. Now we are applying the substitution criteria. First we are substituting the HA with the chlorine, then we are seeing what we are getting. Okay. So when we are substituting the HA with the chlorine, so we are getting the R2-chloropropionic acid, right. So we get this enantiomer compound, and in the next operation we are replacing the HB with the chlorine. Okay, HB with the chlorine here. So in this compound where one of the hydrogen is replaced with the chlorine, then what happens here? We get the S2-chloropropionic acid. Now we will see the configuration of the, right, these two products are different because the R and S are the different configurations here. So we cannot say these are the homotopic nature. Okay. So these are the homomers. So these are not in the homotopic relationship here. Now you can say these are the enantiomers. So enantiomers means where the mirror images, okay, these are the non-superimposable mirror images compounds here, and these are the chiral in nature compound. Okay. So this is called the, where it leads to the substitution leads to the formation of a enantiomer called the stereo enantiotopic ligands. So here some more examples we can see. So in the allyne also we can replace the hydrogens with chlorine or the any other group here. So we get the enantiomers, right. So in like that. So these are some more examples here. Now moving to the enantiotopic phases. Okay. So in here also we can see the hetero enantiotopic phases here. Now here also we can apply the two methods where the substitution criteria and like the symmetric criteria. So here also we are treating this particular, right, acetaldehyde with phenyl magnesium halide, right. So where this acetaldehyde is having the two phases, top phase and the bottom phase, and this Grignard reagent is having the opportunity to attack from the top phase or the bottom phase because both are same. Okay, spatially it is free. So the reagent, it can be attacked from the top phase or the attack from the bottom phase. So when it is attacked from the top phase, so we get the R configuration product here, and when it is attacked from the bottom phase, so we get the S configuration. So we are getting the enantiomers, again we are getting the enantiomer from this particular compound. So these two are said to be the enantiomers. So we will get the, these means there is no homotopic relationship in this particular means criteria here, and some more compounds which are participating in the heterotopic enantiomeric relationship here. So we can take the benzaldehyde or you can take the acetophenone. Okay. So because the attached groups are different, so obviously we will get the heterotopic relationship here.
Okay.
And diastereotopic ligands. Okay. So here the diastereotopic ligands, here also when you substitute the chlorine to this particular olefinic compound, for example here on C1 carbon, when this hydrogen is replaced with the chlorine, so we will get the 1-chloro, it is a propane here. Okay, 1-chloropropane, and the configuration you can see it is a cis configuration, and when you substitute the bottom chlorine, right, so you get the trans configuration. So cis trans isomerization, these are not the homotopic nature. So cis trans configurations are the heterotopic nature, and these are the diastereomers because these two are the non mirror images, non superimposable products here. Yes. And here also you can see some more examples, right. So the replacement of these hydrogens, you get the trans compound here, and replacement of this one you get the cis compound. Okay. So like this, here we get the different products from the substitution criteria. Okay. And here the diastereotopic phases, here also you can check with the relationship of the attached carbonyl group by substitution here with lithium aluminum hydride. So, the lithium aluminum hydride, so it can be attacked from the top phase. So, with the top phase attachment means attack is leads to formation of the equatorial alcohol group here, and the bottom phase attack leads to formation of the axial alcohol. So, axial and equatorial both are the cis-trans isomer relationship here. So, here are the some more examples, and from this toposity. So, why we are study this toposity, why we are checking the toposity relationship. So, first of all, to study the toposity is to see the biological relevance of the atoms and to find out the number of signals in the NMR spectra here, means whether the atoms are having the same chemical environment or the different chemical environment. So, to check these relationship, we are going to know about the toposity terminology here.
Okay, sir. Okay. That means, dear listeners, please understand that without understanding of toposity, and that means what is the homomorphic nature of the ligands or homomorphic nature of units, based on that we are classifying the ligands or units in the within the molecules are homomorphic ligands, homomorphic phases or homotopic phases, or heterotopic ligands or heterotopic phases. Based on that we can understand the asymmetric reaction. Then only we can decide whether the reaction is moving asymmetric way or not. Okay. Now, whenever we are conducting the asymmetric synthesis, asymmetric reaction, the substrate is an important aspect for the reaction. The substrate sometimes chiral, but most of the cases that is the achiral. That achiral compound is transformed to chiral compound after the reaction. Okay. When you consider that substrate, achiral substrate, that is converting from achiral to chiral. Okay. Now, I am asking Dr. Areef, that substrate is converting achiral to chiral, then what we call it as? Suppose if we are assigning some notations to that substrate, how we are going to assign it?
Yeah, sure. So, first of all, let us discuss about prochirality. So, before prochirality, we should understand about what do you mean by prochiral molecule, right? So, I am taking this typical example which is called propanoic acid. So, these both are two hydrogen atoms, and this is the carboxylic acid and this is the methyl group. Now, is it a chiral molecule? It is not a chiral molecule, but if I will replace one of the hydrogen with any one hydroxy group or anything, it will become a chiral. Then this molecule is called prochiral molecule. It is called prochiral molecule, or else it is also called prostereogenic molecule. So, simply we can say that prochiral molecule is nothing but which is a substrate of a chiral molecule. If you replace one of the atom from the prochiral molecule, you will get the chiral molecules, right? So, this is a way of synthesizing the chiral molecules from the prochiral molecules, and this phenomenon is called prochirality. And if you see in propanoic acid, we have three kinds of hydrogen atoms. One hydrogen is present at carboxylic acid. Now, three hydrogens are present at methyl group, and two hydrogen atoms are present at alpha position of the propanoic acid. And these three hydrogen atoms, actually these are three different set of hydrogen atoms. If you see methyl group, three hydrogen atoms are called homotopic ligands, because if you replace them you will get the homomers. But especially there is a alpha hydrogen atoms are there, right? They will play a very significant role. Why? Because these are enantiotopic ligands. Now, what I am doing is, if I will replace one of the hydrogen atom, which is these two hydrogens are close to the observer, if you are the observer, right? So, that is why we are placing these two hydrogen atoms in a horizontal plane. And if you see this carboxylic acid and methyl group, they are away from the observer. So, because of that we are placing them in a vertical plane. So, what I will do is, I will replace one of the hydrogen atom. Just for our convenience, what we are doing is, we are just labeling it as a HA and HB, right? These both are enantiotopic ligands. Why? Because if I replace HA, I will get one isomer, it is D. If I replace another one HB, if I replace the HB, what will happen? I will get a L isomer. So, this D isomer and L isomer of this lactic acid, it is called lactic acid after replacing with a hydrogen atom with the hydroxide group. And if you see this D and L, both are non-superimposable mirror images. So, these are called enantiomers. So, if I replace these two hydrogen atoms, in such cases I am getting the enantiomers, right? So, that is why these hydrogen atoms are called enantiotopic ligands. And whatever the chiral center which is going to generate, so this chiral center is called pro-chiral center, but actually it is not a chiral center. If I will replace one of the hydrogen, I am getting the chiral center, right? So this is the substrate of my chiral center, so that's why this chiral center is called pro-chiral center, and this molecule is called pro-chiral molecule. So this is called pro-chirality. So whenever we are synthesizing, these all chiral molecules are very important. Why? Because all the naturally occurring molecules are chiral molecules. So when we are replicating these all molecules in the laboratory, so in order to study them, it is very important to know, define some symbols, right? So these symbols we will assign for only enantiomers and diastereomers. Enantiomers generally we will study by using RS nomenclature, diastereomers like cis we have, trans we have, and EZ nomenclature. These nomenclature we will use for the study of diastereomers, right? So what I am doing is I am taking this again propanoic acid. So this propanoic acid, this is methyl group, this is OH, right? If I will replace one of the hydrogen, I am getting the S isomer. If I am replacing one of the hydrogen, if I am getting the S isomer, now this hydrogen atom is called pro-S. If I am replacing these hydrogen atom, then if I am getting the R molecule, in such cases this pro-chiral molecule we will give it as a pro-S. So generally R and S nomenclature we will use for normal chiral molecules, and pro-R and pro-S we will use for the pro-chiral molecule which is going to convert it into the chiral molecule, right? So this is in chiral system how you will give the nomenclature of pro-R and pro-S. Same way in double bonded system also we can do, right? So if you are replacing any one of the hydrogen atom, if you are getting the E configuration, then that is called pro-E, or else for example this is the double bond, right? It is also have a two phases. So if a nucleophile, if a electrophile is attacking from the top phase, we will call it as a C phase. If it is attacking from the bottom phase, we will call it as a Re phase, right? So there are certain methods to define, to give the nomenclature of these chiral molecules and diastereomers. So let us see. In that first method is called Hansen method. So this Hansen method, what it will do is, so just we are classifying for our convenience these ligands, and here top and bottom which is away from the observer, two ligands are there, right? So these are called paired ligands, and horizontal line which are close to the observer, these are called unpaired ligand atoms. So you can replace these, unpaired ligands. So what Hansen method suggests that whatever the unpaired electrons, always you should, whatever the unpaired atoms are present, right, these all unpaired atoms you should arrange in a horizontal manner, right? This in Fisher they will come horizontal, right? Matlab whatever the unpaired ligands are there, they should arrange in a close to the observer, and whatever the paired ligands which we are not going to disturb, them, so these are called paired ligands. One is OH and CH3. They should be arranged in a vertical plane, they should be arranged in a, away from the observer, they should be arranged in a vertical column, right? So this is only Hansen method. Unpaired ligands arranged in a horizontal line and paired ligands arranged in a vertical line. Now what I will do is, in order to give whether it is pro-R or pro-S, these are hydrogen atom, right? So as we know EZ nomenclature, as we know CIP rules, Korn-Ingold-Prelog terminology, so what I will do is, if you have a hydrogen atoms, you can't tell whether it is R or S. Why? Because both hydrogen atoms are same, they have a same atomic number, they have a same atomic masses. So CIP will not work. So what I will do is, I will replace one of the hydrogen atom with the deuterium atom. Let us consider that this is a deuterium atom, right? So I have replaced. Now after replacing this one of the hydrogen atom with the deuterium, what now I can assign RS nomenclature. Why? RS nomenclature, CIP rules suggest that first we should check the atomic number. If atomic number is same, in such cases we will check the atomic masses. Hydrogen and deuterium have a different atomic masses, so because of that now we will give the nomenclature to this, and what we will call it as, whenever we are giving the RS nomenclature, so this is a methyl group, this is the COOH group. First you should give the priority to the OH group, after that we should give the priority to the COOH group, after that methyl, after that hydrogen. So after replacing one of the hydrogen with a deuterium, if I am getting R, in such cases this hydrogen atom is called pro-R center. So if I replace another one hydrogen atom with the heavy atom, and if I will give the RS nomenclature, if I am getting the S, then that molecule, that hydrogen atom is called pro-S. This is your Hansen's method. So simple Hansen's method, you should keep all unpaired ligands in a horizontal manner, that is close to the observer, and paired ligands you should place in a vertical line in a Fisher projection which are away from the observer. In the same way, we have another one method which is called Nasipuris method. So in Nasipuris method, what he will do is, these are unpaired ligands, right? Let us consider that this is the OH, this is the methyl. According to the CIP, which is the first priority we will give? OH will give the first priority and methyl we will give the second priority. So in paired ligands, so top priority in a CIP I am placing at top.
Right.
So that's why this is called top. Now let us discuss about the unpaired ligands. So in unpaired ligands, if I replace one of the hydrogen with the deuterium, if I am placing that hydrogen atom, I am placing right side hydrogen atom with a heavy atom. In such cases, that is called right. So overall, in unpaired ligands, top priority is at top. In horizontal line, the top priority is right. So this classification is called top right. Same way you can keep it as a top and left also. Now another one method is, now this is the top priority, right? I am inverting this molecule like this. I am inverting the molecule like this. Now our top priority changes into the bottom, right? Now this is the bottom, and initially which is at right side, the top priority which is at right side, that is coming to the left side. So this way of representation is called bottom left. So there are two ways. Typically, if you are keeping your unpaired ligands at the top, then that is called top priority, and horizontal line, if you are keeping it right, that is called top right. So top right, top left. In the same way, you can also keep high priority group unpaired ligands at the right side, and in hydrogen atom you are replacing to the top one, then you can call it as a right and top, and also we have a left and top, and same way you can write right bottom and left bottom. So these are the few prochiral symbols. So another one is, now let us this is for the typical CH4 molecule. Let us see acetaldehyde. So in acetaldehyde, this hydrogen atom, in formaldehyde I am replacing one of the hydrogen atom with the methyl group. Now these two hydrogen and methyl, these are different, right? So generally this C double bond O group, carbon and oxygen is a more electronegative, so it will take the electron, carbon will get the positive charge, right? So they are very susceptible towards the nucleophile. Now the incoming nucleophile, when I am placing like this molecule, the incoming nucleophile, it may be attacked from the top face, it may be attacked from the bottom face. Yes or not? There are two choices. If it will attack from the top face, I will get one isomer. If it is attacking from the bottom face, these are you will get another one isomer. Matlab these two isomers, they have a different properties. You are getting the enantiomers, right? They may have a same physical properties, but the chemical properties are different. So the properties of the molecules also different, right? So if you are attacking from the top side, right, that phase is called Re phase. If it is that phase is called C phase. If you are attacking from the molecule, matlab you are viewing the molecule from the bottom and the nucleophile is attacking from the bottom side, then that attack is called Re phase attack. If it is attacking from the top side, that attack is called C phase. So this is, if you are generating an enantiomer, then only we will call it as a C phase and Re phase. If it is generating the diastereomers, then the classification will be different, right? So whenever after attacking, if you are getting the enantiomer, if it is attacking from the top phase, that is called C phase. If it is attacking from the bottom phase, that is called Re phase. This is for enantiomers classification. Same way you can classify for the diastereomers also. You can see in the screen. So there is a C double bond O group, right? So we have a tertiary alkyl group which is present at equatorial position, and the incoming nucleophile, it may be attacked from the top phase, it may be attacked from the bottom phase. Initially earlier we saw that if it is attacking the top phase, we said that it is a C phase, right? But in diastereomers it will be reversed. If it is attacking from the top phase, that is called Re phase. If it is attacking from the bottom phase, that is called C phase. So here also you will get two different isomers. Earlier cases we got the enantiomers which have a same physical properties and different chemical properties, but this time we got diastereomers. Which have a different physical and chemical properties which are non-superimposable, non-mirror images. So this is about classification of Re phase, C phase, and everything, prochirality.
Yes.
And let us, that's all about the prochirality.
Areef, you are explained about the substrate molecule as prochirals. Okay. Yeah. When these prochiral molecules are converting into stereoisomers like enantiomers and diastereomers, in the asymmetric synthesis means one of the particular isomer is the major, one of the when you compare to the its counterpart, right? Suppose if the enantiomers are there, E1 and E2 are there, E1 is the major when you compare to the E2, right? How these formation is takes place, what we call it as.
Yeah. See, whenever a prochiral molecule is changing into the chiral molecule, we have a different set of reactions. There are few reactions are there, you will get only one product. So, there is a one prochiral A, just call it as a. After reaction, you will get only one molecule, which is B. Then typically those are called stereospecific reactions. So, there is no problem in that reaction. But there are few reactions. There is a high chance of there is a multiple pathways, not even only one path. If you have a one path, you will get only one product, right? But there are few reactions, we have a multiple paths. Then such kind of reactions are called stereoselective reactions. Yes. So in stereoselective reaction, you will not get one product. 100% if you are getting one product, there is no problem. But in stereoselective reactions, what will happen is you will get more than one product. You will get more than one product. One may be E, another one may be Z. The best example is best example is E2 reaction. So the best example is E2 reaction. So if you see in E2 reaction, which is located in your screen, in E2 reaction there is a chance of getting the two products, yes or not. One is a major product, another one is minor product. So whenever there are multiple possibilities are there, but the reaction is choosing only one path to get the high percentage of the product. Major matlab around 70 to 80% you will get major product, and rest of the percentage is minor. You can see in this Newman projection formula. So in first formula, it is a very stable conformer which leads to the trans product. The second conformer, there is ethyl are adjacent with each other. There is a van der Waals interactions are there, which are also called steric repulsions. So the resultant product is a cis. So that's why the cis percentage is very less than compared to the trans percentage. So understanding stereoselectivity, one of the best example is E2 mechanism. Right, you are getting the two product, one is major, another one is minor. What is the reason? Because if you see in the transition state where the baby alkene is forming, right, in transition state when minor product is forming, there are high repulsions. So that's why the alkene yield is less. But when the major product is forming, the baby alkene, when it is forming in the transition state, their repulsions are very less. So because of that, we are getting the high yield of the product. So stereoselectivity depends on the reaction path, how it is traveling. So this is about stereoselectivity. And also you can classify the stereoselectivity into the different paths while doing the asymmetric synthesis. One is stereoselective substrate selectivity and product selectivity, and again substrate selectivity also classified into different ways, and product selectivity also classified into different ways where we are getting enantiomers, diastereomers and everything. Now let us see substrate stereoselective reactions. A very simple example is what is the use of the substrate selective reactions is, for example, you have two isomers, say A and B. A and B I am using. So I am using another one reagent which is a chiral. A and B are chiral, and also I am using C reagent which is chiral. Now C will react with A and it will form AC, and C react with B and it will form AB, and this AC and AB should be diastereomers. Then you can differentiate the AB. If A is plus, B is minus and C is plus, now plus plus you will get one isomer, plus minus you will get one isomer. This plus plus and plus minus are diastereomers. So these are non-superimposable, non-mirror images, diastereomers, and these diastereomers have a different physical properties. So on a diastereomeric environment you can differentiate the on diastereomeric environment you can differentiate the enantiomers. So that is called substrate enantio selectivity, and earlier slide you can see many examples also. So that is called substrate stereoselective reactions. And let us see substrate diastereoselective reactions. So on screen you can see there are two isomers, one is Z-acetophenone oxide, another one is E-acetophenone oxide. Z and E these are generally diastereomers, and both are undergoing Beckmann condensation, Beckmann reaction. So due to that Beckmann reaction, what is happening, H plus is going to water and it is removing the water, and the group which is opposite to the OH, the methyl group is migrating. As a result we are getting N substituted methyl. In second reaction also Beckmann reaction is going on, and as a result we are getting N-phenyl acetonylide. So we are getting two different kinds of the reaction, right? This is called substrate diastereoselectivity. So that's all. This is about substrate enantio selectivity and diastereoselectivity. That's all. Thank you.
Now I am asking the continuation. What is product stereoselectivity, Mohan sir?
Yeah. So here the selectivity is very important in the asymmetric synthesis. So generally here the product stereoselectivity reactions, that means one substrate molecule when it is forming the two unequal products, unequal percentage of products or exclusive one product is called the product stereoselective reactions here. That means here for example A gives the B plus C. Okay, A is the substrate compound here where it is going to form the two products like B and C here with a different ratio of the percentage here, like B is a 95% and C is a 5% here. Or sometimes what happens here, A gives only B with 100% product here. So generally we call this is the asymmetric synthesis only, and stereoselective synthesis. Okay, and the point to be noted that here all the asymmetric synthesis reactions are stereoselective synthesis reactions,
Yes, 100%.
but not vice versa.
Yes.
Means all the stereoselective synthesis reactions are not asymmetric synthesis reactions here. Okay, means all the asymmetric synthesis, okay, all the asymmetric synthesis are not stereoselective. Okay, so this is the very important thing to be observed here. Now we will see the in this particular product stereoselective reactions. Again we have classified into two types. One is a product enantioselective selectivity and product dash stereoselectivity here. So product enantioselectivity means where that particular the chiral reagent or the achiral. So the reagent it may be chiral or the achiral here. When it is choosing the one of the isomers, one of the enantiomer to give the product, right, stereoselective product, we call the product enantioselective reactions here. Here we will see one example like on this particular reaction where here the glycerol when it is reacted with the ATP, okay, this is the reagent ATP, so adenosine triphosphate. So when it is undergoing the phosphorylation reaction, so among the R and S configuration, so this ATP only phosphorylated with R configuration. That means exclusively it is choosing R configuration to get the phosphorylation here. So it is not reacting with the S configuration. Yes. So it is selective towards its right reactant here. And another example, if you see this particular ethyl methyl malonic acid, this is particular brucine. So brucine is a natural product. Yes. Okay, so it is undergoing the decarboxylation reaction and it is going to form the this particular S2 methyl butanoic acid as a major product here. Yes. Okay, so it is choosing the only S isomer only, but not it is the decarboxylation is not taking place in the R isomer. So this is selective towards its substrate here. That means the reagents, okay, the reagents are selective towards its substrate. Yes. And it is going to form the exclusive product.
The substrate is racemate you are taking.
Yes. Now the enantio phase differentiation reactions. Okay, it is a enantio topos
ligand
differentiation means ligand based. Here the phase means you can say that the phase, whenever you see the phase, that means it is in the sp unsaturation. Okay, sp2 hybridization here, like carbonyl compounds or the olefinic nature here. Okay, so here also we will take this particular phenyl isopropyl ketone. So this particular Grignard reagent, right? Yes. This is the chiral in nature. Yes. This Grignard reagent. So it is going to attack on this particular carbonyl compound. So it have the two choices, like it may be attack from the top phase or the bottom phase here. But here it chooses the sterically less crowded center here. Okay. So for example, when it is attacking from the top phase where the bulky phenyl group is there, so this methyl particular Grignard reagent, it does not attack from the top phase because due to the steric hindrance of this phenyl group here. So by chance it may be attacked from the bottom phase only, because the isopropyl group it is not much bulkier than the phenyl group here. So, it may be attacked from the bottom phase, and it leads to formation of this particular intermediate compound, and finally by hydrolysis it is giving yes 1-phenyl 2-methyl propanol alcohol product here. Okay. So, this chiral reagent is selective towards this particular carbonyl compound here. This is the diastereomeric reaction here. Next, one more example we can see with this particular diastereo selectivity, right. So, where this multi-chiral center compound, okay, this multi-chiral center compound, when we are it is having the diastereo hydrogens here. Okay, we will see this compound generally it is not a it have two chiral center generally, one is chiral center, another is a pro-chiral center, okay, because it is having two hydrogens. So, it is not a chiral nature, it is pro-chiral center, and this is the chiral center here. So, here this pro-chiral center is having the two hydrogens, okay, with labeled the stereo pro-stereochemistry like HRR, and here is a HSR, HRR, HSR. So, these are the pro-chirality symbols here, okay, as the Areef sir explained. Okay. So, we have two options here. Now, in the elimination reaction, okay, so in the elimination reaction you can see in this Sahar's formula. So, where the HRR ligand is going to eliminated as hydrogen bromide here, and it is going to form the trans-stilbene product. Okay. So, it is selective. Okay. So, whatever the reagent, this particular nucleophile, it is abstracting this particular HRR ligand, and it is leading to formation of a trans derivative here. Okay. This is product diastereo selectivity.
Yes. In the entire session of this topic discussion, asymmetric synthesis, we know about the homomorphic units. Based isolation of the atoms or groups from the molecules, we understand the homomorphic units. Based on the homomorphic units, we are classify that units into ligands, homotopic ligands or homotopic phases, and later some of them are classified into heterotopic units, that is heterotopic ligands at heterotopic phases. Based on that, we are classifying the substrate into prochiral molecule. That prochiral molecule, after formation of the product, how that prochiral molecule is arranged at the prochiral center, that is a pro R, pro S or rephase, psi-phase for the phases. Based on that, we are conducting the reaction. The conducting of reaction is also, that is called selectivity. Based on the selectivity, again the reactions are classified into substrate stereoselectivity and product stereoselectivity. That substrate selectivity is also enantiotopic stereoselectivity and diastereotopic stereoselectivity, that is substrate stereoselectivity, and product based on the product formation, product stereoselectivity is classified into 4 types. This entire we are discussed, and in the entire this topic is further continues. We need to characterize or calculate the proportion of the or composition of the isomers formed in the reaction, that is expressed in terms of enantiomeric excess and diastereomeric excess. After characterization, we are also studied about the strategies of asymmetric synthesis. First generation strategy, second generation strategy, third generation strategy, and fourth generation. The first generation is substrate control, second generation is auxiliary control, third one is reagent control, and fourth one is catalyst control. Okay, this is called asymmetric synthesis entire topic. This is very helpful to you. Thank you.